Hello everyone and welcome to the latest installment of the IGCSE 0606 Solution Guide series. In this video we will take a closer look at paper 1.3 from the May-June exam period of 2021. So without further ado, let's get straight into it. In exercise 1 we are supposed to find the values of the constant k such that the following equation has two different real roots. To do that, we will firstly make use of the quadratic formula. Since the exercise states that this equation has two differential roots, this means that the determinant must be larger than 0. In step 1 we will expand these brackets. Thereafter we simplify this expression here, and in the final step we factorize the factor 4k. From there we make use of the fact that a product is 0 in case one of their factors equals 0, and following from there k can either have the value 0 or 1. Next thing to check to determine the possible values of the constant k is to make sure that the result of the determinant is indeed positive, and when multiplying two factors to receive a positive result, each factor needs either to be positive or negative. So this is what we need to make sure of. So in the first case, either k is less than 0 or k is less than 1. And looking at the number line, to indeed make sure that both factors are negative simultaneously, the value for k must be less than 0. Similarly for case 2, where both factors need to be positive, in the first instance we determine that k needs to be larger than 0 or k needs to be larger than 1. And again, looking at our number line to ensure that both factors are simultaneously larger than 0, they need to be larger than 1. Next on to exercise 2, where in part A we need to find the derivative of the expression x squared multiplied e to the power of 3x, x being the argument. Since we are working with a product, we will have to employ the product rule for derivatives. The derivative of x squared equals 2x, and as for the e function we will have to employ the chain rule, thus we will multiply the latter part with 3. Please keep in mind that the derivative of an e function is the e function in itself. So when f of x is e to the power of x, its derivative looks exactly the same. In part B1 of exercise 2 we are supposed to find the derivative of the expression 3x squared plus 4 to the power of 1/3. To tackle this we will have to use a combination of the power rule and the chain rule for derivatives. As for the power rule, our factor will be 1/3, and after reducing the exponent by a whole, our exponent will be -2/3. And due to the chain rule we will also have to find the derivative for 3x squared, which is 6x. After simplifying this expression, 6 divided by 3 equals 2. The following expression provides us with a solution for this part of the exercise. From there, in the second part of exercise B, we are supposed to find the integral of this expression here, which looks relatively similar compared to the result in B1, the difference being that the factor 2 is missing. So to make up for this, when finding the integral we simply multiply our expression by 1/2, since 1/2 multiplied 2 equals 1, and since integrating is the opposite of finding the derivative of a function, it should be obvious that the integral of this expression here is the original function from B1. From there we simply substitute x for the upper boundary 2 and the lower boundary 0 respectively, and conclude that the size of the integral is 0.466. Next on to part 3 of this exam paper, where we are supposed to solve the equation cosecant squared theta plus cotangent squared theta equals cotangent theta plus 9, where theta is in radians and within the interval of -pi/2 and +pi/2 excluded. In step 1 we are employing trigonometric identities to transform the expression cosec squared theta to cotangent squared theta plus 1. From there we simplify our equation and rearrange it for 0. Next we should be able to see that we are dealing with a biquadratic function, since we can imagine cotangent theta to be substituted by x, so our equation would then accordingly look like this. Employing the method provided, we can rewrite the equation as follows, which will help us in factorizing the entire equation. At this stage we can factorize 3 cotangent theta, followed by the possibility to factorize the expression cotangent -2. At this stage we can again exploit the fact that a product equals 0 if at least one factor equals 0, and after calculating each of those options we can conclude that our solutions are either -0.64 0.444 or 0.464. In both cases, we can make use of trigonometric identities again, whereby tangent theta is defined as 1 over cotangent theta. Next on to exercise 4, where in part A we are supposed to find the first three non-zero terms in the expansion of the expression 2 minus x squared over 4 to the power of 6 in ascending powers of x. We are supposed to simplify each term, and to do this we will make use of Pascal's triangle, noting down the first four non-zero terms of the expansion, making sure that nothing escapes our attention, and from there we just focus on the coefficients of the powers of x in ascending order, and we can see that this is the case here. So 2 to the power of 6 could be rewritten as 2 to the power of 6 multiplied x to the power of 0. The second summand relates to x squared, and the third one relates to x to the power of 4. Summing everything up, 2 to the power of x equals 64. Consolidating our numbers here to negative 48. The same thing for the third expression, which consolidates down to the expression of 15x to the power of 4. Part B of exercise 4 follows up on our findings of part A. So here we are supposed to find the term independent of x in the following expansion, whereby the first part of the expansion is the exact same expression that we have encountered in part A of this exercise. So following up from there, we now find the first three non-zero terms of the latter expression. Since we are supposed to find the term independent of x, we can simply focus on the number values, which happens automatically since x squared divided by x squared equals 1, and the same accounts for x to the power of 4 divided by x to the power of 4. Therefore we simply multiply the color-coded numbers accordingly and conclude that the term that we are looking for is represented by the number 879. Moving on to exercise 5, it is stated when e to the power of y is plotted against x squared, a straight line graph passing through the points 2.24, 5 and 4.74 10 is obtained. We're supposed to find y in terms of x. So here we're provided from the outset with two functions, f of y being e to the power of y, and f of x, which is the same as y, equaling x squared. Since we are supposed to find a straight line graph, we need to obtain the two following components. Firstly, we need to find the gradient, and secondly, the y-intercept. The gradient can be obtained by using the 2 points that are provided and simply plugging in their values into the formula for obtaining the gradient. Doing this provides us with the conclusion that the gradient that we are looking for is 2. From there we can find c by employing the general formula for line graphs provided, and from there we can plug in our m as well as the x and y coordinates of either of the points provided. In this case I've opted for the latter point. Rearranging our equation for c provides us with the solution that the y-intercept is located at 0.52. Therefore f of x equals 2x squared plus 0.52, and from there we can plug our value for y into the e function, providing us with e to the power of 2x squared plus 0.52. To find y in terms of x, we employ the natural logarithm to eliminate e, providing us with the solution that y equals the natural logarithm of 2x squared plus 0.52. Moving on to exercise 6, where we are provided with a diagram that shows a circle with center O and radius 2a. Both points A and B are located on the circumference of the circle. Points C and D are midpoints of AO and OB respectively, and the arc DC is part of a circle center O. The chord AB is of length 2a. In part A we are supposed to find the angle OAB, and we should provide our answer in radians in terms of pi. What we know from this triangle here is that it is an equilateral triangle, since the length of each side is 2a. Therefore we know that all of the angles within this triangle are of equal size, namely 180 divided by 3 equals 60 degrees. In the second step we are supposed to translate our angle into radians in terms of pi. Since pi equals 180 degree, we just divide this equation by 3 and conclude that 60 degrees are represented by pi over 3 in radians. In part B of exercise 6, we are required to find in terms of a and pi the perimeter of the shaded region ABCD. The perimeter consists of the following 4 elements. It consists of the chord AB, whose length is 2a. Furthermore, it consists of the lines AD and BC, which are each a units long, and finally it consists of the arc DC, the angle of which we have determined in part A of this exercise. Therefore it can be represented by this expression according to the formula provided. After simplification, we receive the length of the perimeter in terms of a and pi, which is represented by 4a plus pi a over 3. In the final part of exercise 6, we are supposed to find, again in terms of a and pi, the area of the shaded region ABCD. This problem can most efficiently be tackled by subtracting this circled sector from the entire triangle, using the appropriate formulas provided and plugging in the length of the side of the equilateral triangle, as well as the angle in terms of radians. We can conclude after simplification that this area is represented by the expression the square root of 3 multiplied a squared minus pi over 6 multiplied a squared. Moving on to part 7 of this exam paper, where it's all about combinations and permutations. On the outset of part A of this exercise, it is stated that the committee of 8 people is to be formed from 5 teachers, 4 doctors and 3 police officers. We are supposed to find the number of different committees that could be chosen if 1. All 4 doctors are on the committee. Since the order by which the doctors are picked into the committee of 8, we are dealing with a combination, and to ensure that all of the 4 doctors are part of the 8 people strong committee, we need to perform the following calculation, leading us to the solution that there are 70 options to make this happen. In part 2, our constraint is that there are at least 2 teachers on the committee, meaning that there can either be 2, 3, 4 or 5 teachers on the committee, since there are 5 teachers that we can choose from. So it can either mean that we have 2 teachers and 6 non-teachers, 3 teachers, 5 non-teachers, 4 teachers, 4 non-teachers, and so on. So to make our calculations easier, we will be working with complementary probabilities, meaning that we know that the committee consists of 8 people and we have a total of 12 persons to choose from, thus this expression here, and we have 5 options to draw only 1 teacher out of the 5. So to make sure that there are at least 2 teachers on the committee, we need to discard the options for where there is only 1 teacher on the committee. And there are only 5 options for there to be only 1 teacher on the committee. The reason for that being that doctors and police officers combined only make for 7 persons, but the committee consists of 8 people. This means that by design there is always automatically at least 1 teacher on the committee, never 0. This is why we don't have to calculate the likelihood for 0 teachers to be on the committee, since this option does not exist. In part B of the exercise, we are provided with the following equation and we are supposed to find the value of n. Looking at the notation, we know that the value for k in the first instance is 5 and 4 for the second instance. In step 1, we transfer this into the notation using binomial theorems formula provided. In step 1, we just simplify the expression of the brackets in the denominator of the fraction on the right-hand side of the equation. From there we can see that now both sides of the equation possess the exact same denominator, thus we can instantaneously eliminate it, multiplying both sides of the equation by the value of the denominator. Then we rewrite the expression on the left-hand side of the equation to be able to eliminate the expression of n minus 1 factorial. This can be done since n factorial is nothing else but 1 multiplied 2 multiplied 3 multiplied n minus 2, n minus 1 and n, whereby the expression n minus 1 factorial is the exact same thing except for the final factor being n. Therefore we can just eliminate aforementioned expression and can conclude that the value of n equals 6. Part A of this exam paper is about trigonometric functions, and here we are provided with the curve of the form y equals a cosine bx plus c within the interval of 0 and 2.8 included, where a, b and c are constant and x is in radians. The curve meets the y-axis at 0, 3 and the x-axis at the point P and point R at 3 pi over 6, 0. The curve has a minimum at Q and the period of a cosine bx plus c is pi radians. I've provided you here with the visual clues on how we can determine the values for a, b and c respectively using the the information that's been provided in this exercise. To find the values for a and c, we will make use of the coordinates of the 2 points that are already provided. So in the first case, we substitute x and y for the respective values and rearrange the equation for c, receiving the preliminary solution that c equals 3 minus 2a. This will then be used again by plugging in the x and y values into the equation, whereby c will be substituted for the expression 3 minus a. In doing so, we are just left with the variable a, and rearranging it for a provides us with the solution that a equals 6. Now we can plug in the value for a into our previous results, whereby we receive that c equals 3 minus 6, which equals -3. As for the value of b, this can be easily determined since we know that the period of our trigonometric function is pi radians. Thus we divide 2 pi with pi as per the formula provided, and can conclude that the value for b is 2. In part b of exercise 8, the values for the coordinates of p can be determined as follows. Firstly, what we can realize from sheer observation is that its y coordinate must be 0, since it intersects the x-axis. To determine pi, we can simply argue that since the length of the period is pi, and within the interval of 0 and pi included, our cosine function is symmetrical, the y value of p can be determined by calculating pi, which is the length of the period, and subtracting 5 pi of 6 off of it, and we receive the x value of p, which is pi over 6. Our symmetry line would go perpendicularly through the x-axis and through the minimum point q. In the final part of this exercise, we are supposed to find the coordinates of q. Again, since this cosine function is symmetrical within a aforementioned interval, the minimum point is to be found halfway through the entire interval, which would be pi divided by 2, thus pi over 2, and we just plug in pi over 2 into our equation to find the corresponding y value, which is -9. Next on to exercise 9 of this paper. In part A, we are supposed to show that the equation of the curve y equals x squared minus 4 multiplied x minus 2 can be written in the form y equals x cubed plus ax squared plus bx plus 8, where the values a and b are integers. Hence, find the exact coordinates of the stationary points of the curve. Stationary point relates to the equation of the first derivative of our function with 0. So in step 1, we need to transfer this expression into something that resembles the form to the right-hand side, and this is done by expanding both of our brackets. Thereafter, we find the derivative using the properties for derivatives of summons provided. In step 2, we finally equate the derivative with 0, and to be able to factorize this expression, we will apply the method provided. After having rewritten this expression, we can firstly factorize 3x from each of those summons, and thereafter we simply factorize the expression within the brackets x minus 2, from where we can see 2 factors which both are b2 equated with 0, since the result of a product is 0 if at least one of the factors equals 0. Therefore, x can either hold the value 2 or -2 over 3. So these are the x values for both of the stationary points of our curve. To obtain the corresponding y values, we just plug in both numbers into our original equation. In part B of this exercise, on the axis we are supposed to sketch the graph of the absolute value of our function from part A, stating the intercepts with the coordinate axis. Absolute values means that our y values can only contain positive values, meaning everything that's on or above the x-axis. To find the intersection with the x-axis, we plug 0 for x into our function and receive 8, and to find the intersection with the x-axis, we equate our function with 0, which provides us with 2 options, either x being -2 or +2. To sketch our graph accordingly, we need to keep in mind what it would look like without it being in absolute values. So it would have this shape here. Everything that is less than -2 would be on the negative y-axis, which cannot be the case for absolute values of functions. So to sketch out this part of the graph appropriately, what we would have to do is to mirror those points across the x-axis. The final part of this exercise requires from us to find the possible values of the constant k, for which the absolute values of these expressions have exactly 4 different solutions, for which we have to imagine all of the lines that are parallel to the x-axis and intersect this function exactly 4 times. So for example, this parallel to the x-axis would intersect the function 4 times, and everything that's between y equals 8 and y equals 0 without those being included, because for y equals 0 it would only intersect or touch it twice, and for y equals 8 it would do so exactly 3 times. Therefore, k can only intersect this function exactly 4 times within the interval of 0 and 256/27 excluded. Part 10 of this exam paper is all about vectors. Here we are provided with a parallelogram OABC such that vector OA equals A, vector OC equals C. Point D lies on CB such that the ratio of CD to DB equals to the ratio of 3 to 1, and when extended the lines AB and OD meet in point E. It is given that O equals H multiplied OD and vector BE equals K multiplied vector EB, where H and K are constants. In part A of the exercise, we are supposed to find vector DE in terms of A, C and H. So in step 1 we can claim that vector CD can be represented by the expression of 3/4 of vector AD, since the ratio between C and D and B is 3 to 1, meaning that this entire length, which is parallel to AO or A, consists of 4 parts in total, 3 plus 1, meaning that CD must be 3/4 vector CB, which is the same as 3/4 of the vector OA, which is in turn 3/4 of A. Therefore, vector OD can be represented by C plus the aforementioned 3/4 of A, and therefore OE can be represented as H times the aforementioned vector as stated on the outset of the exercise. Consequently, vector DE is the same as the difference of vector OE minus vector OD, and therefore vector DE can be represented by this expression here, fulfilling the requirements for it to be represented in terms of A, C and H. Part B of exercise 10 demands from us to find vector DE in terms of A, C and K according to the radiation theorem provided. Since vector CD relates to vector DB to 3 to 1, vector OD relates to vector DE by the same ratio. Therefore, vector DE can be represented by the expression A plus K multiplied vector AB as stated on the outset of the exercise, and the expression vector AB is substituted for C since vector OC is parallel to vector AB. Part C of this exercise expands on parts A and B, where we are supposed to find the value of H and of K. Since we have in parts A and B of the exercise expressed vector DE in 2 different terms, we can simply equate both of these expressions. Through the entire process, we will leave the left-hand side of the equation as is and expand simultaneously the brackets on the right-hand side of it, and in the second step factorize C and A accordingly. At this stage we can see that K equals H minus 1, since both are multiplied with C, and at the same time that 1/4 equals 3/4 multiplied H minus 3/4, since both of them are multiplied with A. We can firstly easily find H after rearranging this equation for it, and thereafter we can determine H by substituting 4/3 for H in the equation for K. We have now arrived at the final exercise of this exam paper, namely exercise 11. Here we are presented with a line x plus 2y equals 10, which intersects the 2 lines satisfying the equation of the absolute value of x plus y equals 2 at the points A and B. In part A we are supposed to show that the point C with the coordinates -5 and 20 lies on the perpendicular bisector of line AB. Firstly we will attempt to find the coordinates for A, for which we will work with a system of simultaneous equations. We will firstly rearrange both of the equations for x and thereafter equate both of those expressions to find the y coordinate of A. Rearranging it for y delivers us 8, and thereafter we substitute 8 for y in this equation to receive the corresponding x value, which in this case is -6 6, 8. To find b, we will apply the same method as in a, the difference being that we will slightly change our second equation within the system of simultaneous equations, since the absolute value of x plus y equals 2 means that either x plus y equals 2 or that x plus y equals -2. So we will apply the very same method as above. We arrange the equation for y, after which we replace y for 12 in order to obtain the x value for b. Now that we have found points a and b, we can find its gradient, applying the formula provided, and receive in return that the value for m equals -1/2. From there we can find the gradient of the perpendicular, applying the formula provided. What we now need to find is the y-intercept of the perpendicular line, using the formula provided and plugging in our values for m. The midpoint of AB can be determined as per the formula provided. To find the y-intercept of our perpendicular line, we simply plug in the value of m that we have previously determined, as well as the coordinates of the midpoint of AB. Rearranging it for C provides us with the y-intercept, which is located at 0, 30. Therefore, the perpendicular line can be represented by the expression 2x plus 30. To figure out whether point C is located on the perpendicular bisector of the line AB, we plug in the coordinates of C into the function of the line and determine that both sides of the equation are identical, which proves that point C is indeed located on the perpendicular bisector of line AB. In part B of the final exercise of this exam paper, it is stated that point B also lies on the perpendicular bisector. M is the midpoint of AB. The distance CD is 3 times the distance of CM, and we're supposed to find the possible coordinates of D. So in step 1 we will determine the vector CM by subtracting the coordinates of C of the coordinates of the midpoint of AB, receiving -5, -10. Since it's stated that the distance CD is 3 times the distance of CM, we will have to add and subtract the distance of CM from C in order to find both of the possible coordinates of D. After simplifying both of our calculations for D1 and D2, we will conclude that the coordinates are -20, -10 and 10, 50. I've been your host Marco from Planet Maths. Should you derive any value from my videos, please consider to leave a like, comment and subscribe. Thank you for watching. Cheers.